This is the seventh and final lecture on Text Unit 7 on molecules and bonding. This is the second of two lectures on molecular orbitals. This one is specifically concerned with diatomic molecules, which are molecules of only two atoms. The simplest diatomic molecules can be found in the first row. We began the last lecture on electrons and molecules by considering H2. Remembered that each H atom has an electron in a 1s orbital, and stated that the shared electrons occupy a molecular orbital made by adding the two 1s functions together. The result is a sigma bonding orbital. This is all review up to this point. You'll remember in the last lecture that every time two orbitals interact that are combined mathematically, two orbitals result. And if three orbitals interact, three orbitals result, and etc. So if we take two atomic orbitals to make a bonding orbital, it makes sense that we could take the two atomic orbitals and that they should produce another, or that another possibility should exist, and that is the anti-bonding orbital. In other words, when the sigma bonding orbital is formed, an anti-bonding orbital also arises from the combination, and this in particular is the 1s minus 1s combination in this case. The shape of the orbital after subtracting 1s from 1s is like this. Here is a lobe here, here is a lobe here. These dumbbells or lobes are not between the hydrogen atoms. So the pair of if a pair of electrons is in an anti-bonding orbital, it would be here or here. Hence the name anti-bonding. There are no bonding qualities to the orbital. Naturally, anti-bonding orbitals are destabilizing and high in energy, whereas bonding orbitals stabilize the molecule or lower in energy. So here is a very typical energy diagram for diatomic molecules. Here are the energies of the 1s orbitals before the molecule is formed. Here at a lower energy is the sigma bonding orbital. And here at a higher energy is the anti-bonding orbital. Okay. Again, just as in polyatomic molecules, making molecular orbitals essentially removes atomic orbitals from existence. In other words, they're gone and the molecular orbitals are there. So the two electrons in H2 will go into this sigma bonding orbital. Right. For this type of orbital diagram for molecules, which is what this is, the bond order can be defined as being equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So you could look at this diagram for H2, see two electrons at a bonding orbital. The bonding orbital is 2 minus 0 over 2, or 1, which is the same bond order you would predict by drawing a simple Lewis structure for H2. It's possible in laboratories and in interstellar space to stick an electron to H2 and form H2 minus. We could understand this with the same sort of orbital diagram. It's got one more electron, 3 electrons. 2 go into the bonding orbital. 1 goes into the anti-bonding orbital. The bond order of H2 minus is 2 minus 1 over 2, or 1/2. So adding the electron to H2 reduces the bond order from 1 to 1/2 and weakens the bond. Before going on, answer the question, what would the bond order be in an He2 molecule? He2 has 4 valence electrons. 2 go into the bonding orbital. 2 would go into an anti-bonding orbital. Resulting bond order is 2 minus 2 over 2, or simply 0. So this molecule would have a 0 bond order or no bond. And this is why, or one understanding of why, He2 diatomic molecules are never found to exist. Right. If you can work with orbital diagrams for the first row, there is a straightforward generalization to diatomic molecules made up of atoms in the second row of the periodic table. For example, a pair of two s orbitals combine to make sigma and sigma star orbitals. And I'm considering the two s orbitals because the two s orbitals and the two p orbitals are the valence orbitals in this case, the ones involved in bonding. A 2p orbital can also make sigma and sigma star orbitals. In other words, 2p orbitals in a molecule can combine to make a sigma bonding orbital. We've seen the sigma bonding orbital before in the last lecture. But naturally, an anti-bonding orbital is also possible. Okay, so 2s orbitals make bonding and anti-bonding orbitals in a way similar to the 1s orbitals did. And 2p orbitals also make sigma and sigma star orbitals. In addition, second row p orbitals that do not point along the bond, that are perpendicular, can be used to make pi bonding orbitals, something we saw in the last lecture. But at the same time, it's also possible to make pi anti-bonding orbitals. And again, we see that also, while pi anti-bonding orbitals have all sorts of crazy lobes where electrons can be, the electrons are nowhere near between the two atoms. Whereas here they're at least above and below the two atoms. So pi orbitals are stabilizing, and pi anti-bonding orbitals are not stable. If you consider an orbital diagram for the second row, here we find the energies of the bonding and anti-bonding orbitals made from the 2s orbitals. The 2p orbitals are higher in energy than the 2s, and they make pi orbitals, sigma orbitals, pi anti-bonding orbitals, and sigma anti-bonding orbitals. All of these orbitals being higher in energy than this sigma and sigma star orbital. So diatomics made from the second row will have electrons in an orbital situation like this. Well, there are some such differences in energy for different diatomics, but we'll assume for this lecture that they all fall into an orbital distribution like this. Let's see. So, again, for second row diatomics, core electrons remain in 1s core orbitals, don't engage in bonding. So those are closer to the nucleus, not even in the picture. Valence electrons go into molecular orbitals made from the valence atomic orbitals. Alright, referring to the energy diagram on the last slide, you should be able to make orbital diagrams for N2 and O2. Here is N2, for example. There are 2, 4, 6, 8, 10 valence electrons. 2 go here, then 2 go here, and then 1, 2, 3, 4 go here. 2, 4, 6, 8 electrons in the picture, and then electrons 9 and 10 go here. Now, 2 of these electrons, these 2, are actually in an anti-bonding orbital. The remaining 8 are in bonding orbitals, so the bonding orbital is 8 minus 2 over 2, which is 3. You'd see if you were the same bond order if you refer to the Lewis structure for N2. In addition, all the electrons in the N2 molecule are paired. Now, this state is referred to as a diamagnetic state. When a molecule has all its electrons paired, it will have no magnetic properties. This is what diamagnetic means. Diagram for O2 adds 2 more valence electrons because O2 has 2 more valence electrons than N2. The total is 12. Here are the 11th and 12th electron. Notice we still apply Hund's rule. Put 1 electron in each orbital in a collection of a given energy until all the orbitals are half filled. Then pairing can take place. The bond order, 8 minus 4 over 2 is 2. That's the same as you would predict from the Lewis structure. However, the Lewis structure, if you look back at it, will tell you all the electrons in O2 are paired, whereas in this picture, clearly they are not because of Hund's rule. Okay, this is an example of a paramagnetic molecule. In other words, because of these unpaired electrons, O2 actually has very weak magnetic properties. I have to make O2 into a liquid, very cold, to actually observe O2 interact with a magnet. These are very weak properties. For review, the bond order was found because there are 8 bonding electrons, 2, 4, 6, 8. And there are 4 anti-bonding electrons, 2 here, and these 2 in the pi star anti-bonding orbital. Heteronuclear diatomics, in other words, different atoms or atoms of different elements, can also be understood with these orbital diagrams. Here's one for the NO molecule, which comes out of your car exhaust. There are a total of 11 valence electrons, 2, 4, 6, 8, 10. Here's electron 11 by itself up here. This molecule has an unpaired electron, hence it's called paramagnetic. Another way of thinking about molecules with unpaired electrons is to call them radical. Often these molecules are highly reactive, and NO is an example. The bond order is greater than 2 but less than 3. 8 minus 3 8 bonding electrons minus 3 anti-bonding electrons over 2 gives a bond order of 5 halves for the NO molecule. Alright, this concludes the 7th and last lecture for Unit 7 and the second lecture of 2 on orbitals for molecules.